Tobias Ruck. He's the Chief Technical Officer of the TixTown ticketing app, event tickets. And he's also a software developer who's been working for many years in Bitcoin Cash and now eCash. He's done many interesting projects over the years, but significantly from my perspective with eCash, he's contributed a bunch of important infra projects, such as the chronic in-node indexer, which is an important part of our infrastructure now. The ALP protocol, which is a good token protocol, is basically a better version of SLP, and the Agora protocol, which is now becoming popular, including all the infra libraries and stuff that makes it so people can build stuff on it in a good way. And today he'll be talking about a potential new transaction format for eCash.
Yeah, so hello everyone. So this is not really like a proposal or anything, but just to get like people up to speed on all the intricacies that were like discovered over time. So let me try this. No? Do I have to turn it on or something? No. Yes, there we go. It just takes like a few seconds. So transaction format. There we go. So it's basically like 3 reasons for a new transaction format. Very high level. First of all is efficiency. For me personally, this is the most important because I want eCash to be able to scale for like, I don't know, millions of transactions per second, presumably. Who knows where it can go. But I think that should be like the high goal that we set ourselves. Second one is fixes. Those are also important, obviously. Some we can live without. But it would be great if we can, while we're doing it, also do some things that kind of need to be fixed. And then the last one, and that's obviously more optional, that would be to add new features that just previously weren't quite possible. So that's also quite exciting. So the first one, efficiency. And at the end of the day, doing more transactions per second on less hardware, or whichever way you calculate that. The first one, and these are like, I'll get into these. The first one is that we split the validation from the validation of the transaction itself to whether the coins even exist, so that we can do validation without I/O. I will explain why this doesn't work right now. Second one is a UTXO hash set. So instead of storing just full UTXOs with all the data, script, and so forth, we just store a hash of that. The next one is something, I'm not sure if anybody heard of that yet. It's a compact transaction. And this is a very efficient internal format for the node, which allows to very efficiently commit to the database. I'll get to that. And the last one is just a smaller integer coding. I think this is one of the first blog posts that Amelie wrote on how to scale stuff. It's not like you'll see the numbers and it's not like crazy, but it's just something like, why not do it if like that's already a thing. So for the first one, how does validation of transactions work today? Status quo is there's 2 neuron trips. This animation. So we basically have a 3-step process for every transaction. The first one is you get a transaction and then you first look up all the UTXOs of that transaction. The next one is you verify the transaction, given that UTXO data. And then the third step is like, okay, the whole thing is valid, it got mined, whatever. Now we can write the UTXOs to the DB. Of course, that's like grossly simplified, but this illustrates the point that I'm trying to make here. And the problem is, this is fine if it like, the whole thing is local and you have like a cache of UTXOs and so forth. You can kind of like get around this relatively easily. But once you start to like shard the whole system, and you really need sharding to go to really high transaction numbers, then you can really see how like, okay, this UTXO comes from there, it comes from there. Like the whole organization becomes really messy, especially if you have to do it 2 times. So how do we fix it? Exactly. So this is how a transaction looks like stripped down to like the core essence. What would be great if I didn't? Okay, I think we're good. So we have the transaction. We have outputs. We have out points, which basically just point to a UTXO or a previous transaction output. And we got the inputs. And the really one thing we need to do, which there was an animation, is okay, it moved to the round. Can I like still wait around that? Okay, I guess there we go. So basically, what we do in the input, we add the output that is being spent. We basically just add the UTXO into the input, and you're like, okay, like that just adds redundancy. But what it actually does, it simplifies, like it removes the first step basically. So remember this thing. So the left one is like, it should have been like blurred out, like the transparency didn't quite work. So that should be like strike through because it's no longer step one. The step one is now verify transaction, which is great. So the very first thing we can do when we get a transaction, we can just verify it. And we can do that completely independently. Like someone could just give you a transaction and you can verify if all the signatures, all the hard work checks out without doing any database lookup, no cache lookup, no nothing. And this also means this can be hyper-parallelized. Like this can just be like the very first step. Any processor just gets that and say, okay, this is fine. We can move into the next step. And then after that, we only have to check if the UTXO actually exists and write the result to the DB just in one go. There's no like look up, then go back to process it, and then go back again, which really simplifies things. But wait, there's more. Because we simplify the first step, we don't need all of that validation data during the processing of the thing. So what we can do actually, we can compute enhance, yeah. So this is the 1 second. So this is how the database of the UTXO, which is the most important thing. In order to run a UTXO blockchain, you need to store all the UTXOs. The way you store the UTXOs normally is you put, you have like a map from the where this output lives to all the data of the output. But what you can do if you in the new DB is a hash set. So instead of storing the data, you just store the hashes, and obviously that will be much smaller. So you can see here it's 64 bytes per UTXO, and in the hash set or more, 64 is like the lower limit. It can even like 100, or if you have like really big UTXOs, it could be hundreds of bytes. But if you only store the hashes, then it's only 32 bytes per UTXO, no matter what's in that UTXO, because it's only a hash, and that is really simple to handle because everything's the same size. You can allocate it very easily. You don't have to handle anything dynamic. So that's really cool. And there's even more. So what we can do is after we did all the validation, we can compact the transaction so that we have all this machinery here, but we can only calculate the hashes of the UTXOs as they are in the UTXO DB, and then we only have the input hashes and the output hashes, and that is much more compact. You then send that off to the processor, and you have much more memory that you have to juggle around, and especially for bigger transactions, this becomes and especially with transactions that have a lot of data in them, this becomes much smaller. So this is from the Project Hamilton white paper. This is how it actually looks like. On the left, we have this hash set. It's just hashes, and then the this is how it looks like non-compacted. So we have the normal stuff from a transaction ID, where the output comes from, the script basically, how much dollars there are in there. Same thing here in the outputs. You can see that's perfectly equivalent. And then what the inputs do, they basically remove the hash of that, and the outputs, they add the hash of that. And this way you have a very easy, very fast way of updating the UTXO set. And there's no, like this data, like after validation, like you can basically internally to the node, you don't need it anymore. Like you don't need it for the next step, which is the hardest step, because that is like where the actual database interaction comes in. So that's really cool. Then also, in code, this is to make integers a little bit smaller. So one thing we observed is that integers are usually small. So for example, this looks really horrible, but maybe we can decipher it a little bit. So this is 10, except with a new line in between. That's how we write it in Germany. And basically outpoints are usually like 10 or less. I mean, sometimes you have like really large transactions, but it's usually 10 or less. But the range that we allocate for this is like 4 billion, right? So most of that is kind of like unused, basically always. Then the same for output values, like how many satoshis something has. This is usually like 100 million or less, but we allocate like 9 trillion or something. 10 to the power of 18 or something like that, which is upper range. And most of that, again, is wasted. Version, even worse, there's always less than 3, but we have the 4 billion range. Log time also is usually set to 0, and we also have the 4 billion range. So what can we do? We encode things smaller. So we encode small integers smaller. So if the value is very small, so between 0 and 127, we just encode it in one single byte. And if it becomes bigger, we encode it in progressively more and more bytes. And really large numbers, I encode it with like 9 bytes. So what's the impact of that? What is this all worth it? And this is really blurry. So if we do, fixed is how it's right now, the way I described it. And then here, just for comparison, I also checked if compressing it changes anything. So we don't like do some kind of compression that we could just easily do by just using some simple compression algorithm. And this in the case is LZ4. It's like to cross-check if we added some kind of entropy. So this is this, and fixed is here. Yeah. And there it's 0 because that's the baseline. So if you do fixed, you don't have any compression because that's the baseline. If you then use compact size, which is the integer encoding used by Bitcoin for like sizes, you get quite a bit of compression. But if you use encode, the new one, you see you get quite a bit more, just a little bit. But the numbers are not too big. It's like 3, a little bit over 3%. But if you have a really, really large volume, if you just get 3% more efficiency in a really large system, that can mean a lot of resources. And there's not like a huge downside. Like, it's just a different function call, basically. So some fixes that we can do. So this was all the efficiency stuff. This all ties in a little bit, so everything leaks a little bit into the other stuff. And one thing that Mathieu already mentioned is the SegWit, or rather the transaction malleability fix. And this has a practical implication because chained transactions become malleable. So if you have like a chain of transactions and you want to design some kind of protocol using that, basically anyone on the network under certain conditions could just invalidate the transaction ID of the previous ones. So let's say we have this one, and this is like the thing we agree on, but then someone else comes along and changes the transaction ID of the previous one, and then this one becomes invalid and you can't use it anymore. And as Joey might be able to tell you, there's like a lot of cases where you want to have chain transactions that you like kind of do as one thing, like in order to pay out or whatever. And if then people are able to malleate that in some way, it usually doesn't happen in practice, but it's just good to just avoid those problems. So there's a really easy way to do that, to fix that. And it's simply to not include the signatures as part of the transaction ID. So this is just straight up from Bitcoin. But we can do the same thing where you sign the transaction with the private key. Normally, if you change the signature, the transaction ID becomes different and the link doesn't work anymore. However, if you excluded the signature, then there's not really a way to change the transaction without also invalidating the signature, because the signature signed perfectly all of this. So okay, great, like we fix chain transactions. It's not that incredible, but wait, there's more. And Mathieu already alluded to that. I'm not sure if I'm going to use this again in this presentation, but because there's actually something that we can do with just fixing that. And this is already quote-unquote live on Bitcoin. It's called a covenant attested token. I think this is just like a backronym, which is like an acronym that you just find a few words for, because they wanted to call it CAT protocol. And the essence is that you can do miner validated tokens by simply having OP-CAT. I mean, this is for Bitcoin. For us, the reverse is like, okay, fractal Bitcoin, whatever that is. And, okay, so looks good. And here we can see that on BTC, yes, they have SegWit. On Axis, we don't have SegWit, but BTC does have OP-CAT. It does not have OP-CAT, but BCH has OP-CAT. Therefore, they both can't do OP-CAT tokens, I guess, or CAT tokens. Whereas on Lotus, actually, we have both Malfix and OP-CAT, so there it is possible to do to do these tokens. It's just that people just haven't come around yet to do that, but it is in theory possible. And then you would have miner validated tokens, just like cash tokens, to just would be a little more harder to use, I guess. And it's okay. No, just separate thing, but maybe a little bit like SLP more. But yeah. So, but miner forest tokens, like why? Like the Bitcoin Cash people are like, oh, this is like the best thing since sliced bread. Cash tokens, eCash is like, like SLP and LP. This works like perfectly fine. Why would we change this perfectly running thing for something better? So I think it's really important to address this. One thing that a miner and forest tokens does is that you immediately get simplified payment verification using, if you have miner and forest tokens. You get something, you get a Merkle tree, and you do the proof of work check, and they know for sure that this is a valid transaction in the chain. So that enables like Electrum ABC. It has the same security properties that it had before. Whereas if Electrum ABC would add tokens now, they would be like, well, everything is like checked super secure with like normal Bitcoin assumptions, except token balances. Those are like trusted by the indexer. Also another thing, which is sometimes overlooked, is PV proofs can also prove to another blockchain that a token exists on that blockchain, because we have the proof of work. You get the proof of work, you check if it's valid, you check the leading zeros, and maybe you do that a bunch of times, and then as long as the thing you're getting in return for that, like a payout or whatever, is smaller than a proof of work you would have to spend in order to fake that, that's economically secure. So that's something that you can do, and you could do that with cash tokens in theory. You can't do that with SLP. Another thing is, and eCash added this very recently, is assume UTXO. And I think this is a really, really important thing. Really happy that eCash is spearheading this. It's back for the put it from core, right? It's not like we came up with all that. But if we had assume UTXO, it would be incredible for new businesses who are like, oh, let's do tokens. But let's say in like 5 years or 10 years, the blockchain is like humongous because suddenly everybody in Saipan starts using eCash, or the whole world, whatever, then the blockchain becomes really, really heavy. And in order to do tokens, like right now, I don't really see a way how you could avoid just verifying the entire history, at least of that token. But if you have Assume UTXO, you can just bootstrap from the current UTXO set, which grows with the number of users, not with the number of users times time. So you just download the UTXO set, you know for sure every token balance in there has a certain value. Chronic can index that, and you're good to go to just immediately start making economic activity with that. Then something that probably Joey occasionally has to hear from users is like, why no buy orders for tokens? Or like, hey, I have this many XEC, I want to buy some kind of token. This doesn't work because Agora only goes from token. You put up a token on the market and someone accepts it using XCC. But miner forest tokens, you could just do the same procedure as Agora currently does for the reverse, right? Someone puts up XCC and you get tokens in exchange, or token for token offers where it's like, hey, here's some, I don't know, MUSD. Can you exchange that for, I don't know, TUSD or something like that? And then something that is also very, very interesting, I think, this gets into the DAO area, where you're like, oh, I just want to create like a quote-unquote business. I want to issue shares. But then where does the money go to? You could just have someone just designate, hey, this person, they're like the treasurer, all the money that got invested goes to this guy. But, if the DAO is more loose, then how do you enforce that guy actually does what he needs to do? And with miner and forest tokens, you could, for example, lock XEC in a UTXO that can only be spent if 51% or more or whatever of some miner forest token vote in favor of that, and you can check that on chain. I mean, guys on PCH are probably aware of that. I don't think many people did that yet, but that's definitely something you can do. And this is just completely impossible using SLP. You can't do even to start to think about that. You would have to have some kind of custodial mechanism, but with this way you don't have to do that. Yeah, you can just trust the network, so to speak. Then some features that we get, and this overlaps a little bit into efficiency. And here's 3 of them. The first is flexible transactions, or flex trans, but I don't quite like that name. It sounds kind of gay. Then we have transaction introspection opcodes. Mathieu already mentioned that a little bit. And then also this thing that I call Preamble. I haven't seen this anywhere else mentioned yet, and I had no reason to change that name yet, and it kind of sounds cool. But these all have some very interesting properties that, may be helpful. So the first one is flexible transactions. And the purpose of that is basically to future-proof the transaction format. So new fields can be added. So, this is the current transaction format. And it's cool, right? There's some things there. But there's lock time and sequence. The other ones, they're kind of logical. But the lock time is just it's clearly just added on top of the transaction system. Where it's hey, wouldn't it be cool if you also could lock when this transaction is valid? And the same with the input. It's hey, wouldn't it be cool if you could limit when this input is spendable, basically, or can spend the UTXO. But what if someone comes along and wants to add more fields, right? And then what do you do? Then you're okay, well, very easy. For example, if you want to add the height of the input you're spending, there's some cryptographic things that you can do with that. But let's just assume this is useful. someone wants to add that, and you change the transaction transaction format again. And it's like, okay, great. So now you go through the same hard process to upgrade the transaction format, which like everybody has to do. Not very good. Or someone comes along and is like, hey, how about we also add some payload to replace OP return or whatever, or whichever other idea you would have. Then suddenly you have a new transaction format for every little change. So that's obviously a very bad idea. Don't do that. So what FlexTrans does, it makes it so that the transaction format can add new fields if needed, without having everybody like requiring to update every time. And the way to do that is basically to, it's cut out a little bit, but I can say what it says, to everything that like might get new fields, and you can see I replaced the other fields with that metadata. You add, or it's almost like a dictionary. Okay, there's the keys, these are the properties, and then the payload is the actual data. And then you just assign for every type, it's a number, you just assign some meaning. So this is just, I don't know, not very important what the exact numbers is. This is just something I slapped on the slide. So you could say, okay, type 0, that's the height. Type 1 is the height log. Type 2 is relative time log, whatever. Or if you have number 64, it's bytes. It's bytes for the memo, right? To add like some kind of payload. And now you're like, okay, why is 64 so far down? Because one thing that I think is a really good idea is, in order to avoid having to redo the whole, and there's a new field, everybody has to update now. One thing that would be really good if those are already pre-standardized, so that you know exactly how big each field number is without it even being assigned like any meaning. So okay, I read the number 2. Okay, that means there's an integer following. Oh, I read a number, I don't know, 500. That means there's bytes following. Maybe it's not assigned a meaning yet, but this means everybody can parse the transaction format without like having to know what the specific meaning of every type is. And this also means that, for example, a wallet, if they don't know, like they get in a transaction, they can still parse it and handle it without knowing what the type byte is. So it wouldn't break previous wallets, even though we kind of amend the transaction format. Of course, miners and everybody who's like who needs consensus, they would say, hey, I don't know this type bit, reject it, right? Whereas a wallet could say, I don't know this, but it's confirmed on the blockchain, seems fine. They probably know what they're doing, the miners. So that's that. Then transaction introspection opcodes. We have them on BCH. We don't have them on XCC really. We don't really need them on XCC right now because we have object datasig. So let me show that real quick. So this is from Agora, the Agora code. And at the very end of the contract, you can see we do a check datasig verify on the pre-image of that is being signed. Then we do some byte shifting, and then on the same signature and public key, so these are all the same, we do a check sig. So this means that this pre-image for sure points, or like is the pre-image for the transaction. This is ensured by object-sig. But it would be great if we could simplify that. So here are just some suggestions. I don't know, very relatively simple. Everything, I mean, they are pretty much live on BCH. The thing with BCH is that they kind of built their opcodes on their current transaction format. But I think that's the wrong order. I think you should first build a really nice and final transaction format. We're like, that's the one we go with. And then afterwards, you pick the opcodes that naturally emerge from that design process. And you can even design them in union. I mean, I don't need to go into details with these. These are just some suggestions. But the most important ones is that you can get the out point of your own thing, that you can get the output that you're spending, and that you can get of any input, and that you can get the output of any output of a transaction. And that way you can, for example, if you use pick output, like for Agora, for example, you can be, does this person actually send the tokens to the seller of the tokens? And right now we kind of have to do that with the trick from the previous slide. So that was that. Now there's the preamble. So this is kind of a wild idea. But I think this is extremely powerful. And let me show you what you can do there. And there's actually many things you can do with that. So from the same video that Mathieu was referencing, the one big problem why you want miner enforced tokens and why we currently can't have SLP or ALP buy offers is that a contract or a UTXO or a script, it cannot verify that something going in to the contract is a valid token. Like, for example, that was back in the day where USDH was still a thing. If you're like, hey, here, I have 4 USDH, do something with that. The contract has no way to verify that. It just cannot know that. I mean, it could verify all the transactions back to Genesis, but that would be so incredibly expensive that it just kind of breaks. Like, there would be blocks just filled with validation transactions of that. So that won't really quite work. So what one ways around that are exactly, for example, there's this CAT protocol that I mentioned before, and that would solve that, right? As I mentioned before, this is a solution to that. Another solution is cash tokens, right? Anybody? No? Which also solves that. Okay, the title is wrong, but the content is correct. And basically what cash tokens does, in the output, it just adds the token data. It's like, hey, here's the hash, the token ID. They call it category ID. Why not? Some extra stuff, some NFT stuff, especially fungible NFTs, and the amount, how many tokens are in this output. There's a really simple solution, but you just throw it into the transaction format. It's like, okay. I mean, I'm very biased. I'm not like terribly impressed. I mean, it's a solution that works, right? But like, you just bake the transaction format into the consensus. So it's like, okay, I guess. So something that I identified is the scale of miner enforced tokens on like level of confidence in their own protocol. So SLP ALP is like very, how do you say, humble, so to speak, where it's like, hey, we don't do any consensus change for this. This is purely actually the text is wrong. I don't know what happened there. This is just, we know this works already. We can just deploy this on the blockchain. No changes needed. The next one is probably like CAT tokens, where it's like, well, this requires a change that is totally useful for other reasons already. Like, there's no reason not to add OPCAT to BTC other than like esoteric reasons, because OPCAT is extremely useful for all kinds of things. Or for us, SegWit, there's other reasons to do SegWit, not just tokens, obviously, because you get some fixes, some benefits from that. And actually, one of the first Bitcoin Unlimited improvement proposals. So there's BIPs that are Bitcoin improvement proposals, but the Bitcoin Unlimited improvement proposals I saw from Amaury was exactly a transaction format that would fix SegWit. And then on the other side of the scale is cash tokens, which is the ultimate protocol. The devs are so confident that this cover all use cases ever. We will never ever need something new in there. But personally, I'm skeptical. I don't know. If you want to do some change, then you have to do another consensus rule change. which is annoying. So yeah, if you don't cover everything. And one thing that we know, some things that are already not covered, which is cash tokens. It cannot do mintable tokens properly. Like you can like emulate it, where it's like, hey, you have this one pool where they're locked in, and then like you have some kind of secondary token that you can kind of drain tokens out of that UTXO. But if you create a new token, you have to create all tokens that would ever exist, ever, in one transaction. And then those are the tokens you have. And no more can be minted, basically. Which is a huge trade-off. And I don't know, it seems to create some problems. Like if we were to tell Tether, hey, you have to mint all 9 quadrillion tokens you ever want to have at the very beginning and then drain them out of your thing. I mean, maybe that would be cool. Yeah, they'd be fine with that, but it just seems a little bizarre. And in theory, you would eventually hit the token limit where you just used up all tokens, like you burned all of them through the process of recycling tokens, that the token's just dead, right? Like you have no more tokens, you used all of them up. And, that's kind of scary for a token issuer that could happen, even if the number is very high. So is there like something in between, right? We're all common sense, moderate centrists. Like, would be great to find something that's like applicable to everybody. Oui. Oh, you just. Oui. No, heresy, total heresy. Yeah. So that's exactly my opinion. Don't assume that, right? Don't assume that what you think will be the last thing to cover all specs. Always like carve out something where here can iterate, there can iterate without breaking everybody again. Like if changing a transaction format, it breaks everybody. Literally. I mean, not physically, but like mentally. Like their software breaks basically. So this is just something that we can do like once, like ever, until the end of time, which is quite far away. So yeah. So the solution to that, in my opinion, are the preamble tokens. And you can see the alignment is still beautiful. And there the idea is a little bit similar to cat tokens, but a bit more intentional. We just add like minimal primitives to make tokens convenient. Because cat tokens, like, they're just like kind of forcing it. It's okay, we can just barely do it. But with preambles, I think this would be a small generic change, which also has other use cases. Like without just being like, this is the final token protocol. It just gives us the tool set to do other kinds of token protocols, or like a whole family of token protocols. So how does the preamble work? This is again a screenshot from my video. You can see it applied YouTube compression and then all kinds of other compressions on top of that. And now the projector is projecting it. So sorry about that. But the idea is basically that you just add this preamble in the transaction, which kind of like it's a script that runs on the transaction itself. Like the input basically is the transaction and just like does a check on the transaction itself. Whereas inputs, they check the transaction itself, but mostly they check the output that you're trying to spend, because that's the whole point. You're like, okay, am I allowed to spend this? Whereas the preamble is more like, is this transaction, does this have certain properties that are desirable? And what the preamble for a token script would check is, do all the inputs tokens, like let's say we have three here and 1 here, does the sum of that, is it bigger or equal than the outputs? In this case it is, so there's only 4 here, and there's 1 here and 3 here, so this check would work. However, if I were to change this to 4, then this check would no longer work, and then this script here would fail, and the whole transaction would be invalid. So here you can check that, but how does this work? Does this check that this actually has 3 USDH? Because a script can't check just by itself if the input is valid, like it could be a forgery. But that's where proof by induction comes in. I don't want to get into that much, but basically what the script here can check is if this input also comes from a transaction that has the same script. And then you just go back and back and back. Like the script only has to check this one to check the entire history. That's why it's proof by induction. You only have to check this one step. You only have to check one step, and you get all preceding proofs as valid. It's a little short because I don't want to get too much into that, but the idea is basically that you can ensure that works. And that's basically how cat tokens work, except they do it in a very roundabout way. Yeah. And that is very efficient. So what would this entail to the transaction format? So here, remember this. I stripped out some of the details. And then basically would add preambles, which are just like inputs without a UTXO that's being spent. And they just have the locking script and the unlocking script right next to it. Then the locking script, which would basically be the check, do the tokens balance, right? Do you create tokens out of nothing, or do you don't? That would be the hash. So the hash of this would be like the token ID, so to speak, of the whole thing. And then here we'll put the amount, so that, okay, this is the amount of tokens that are part of this input. And the same for outputs, and here the preamble amount is missing, so this is a mirror of that. It's just cut out because of Google Slides. Then we also would need some opcodes, so to get the preamble hash of something. But then these are relatively really efficient and simple opcodes. And they basically are like, okay, give me a preamble hash, and I will return you the sum of all the inputs that have that hash. See how many tokens are in the inputs that have this hash. And here the same thing. How many tokens with this token ID summed up have this hash in the outputs. And then you can do non-inflatable tokens, which are just normal tokens, right? Tokens you can just do, like you have to have them in order to move them. You can't just create them out of nothing all the time, which would be, not that useful. But then you can see that this is basically the entire preamble, or like the meat of the preamble. It's like, hey, how many tokens are going in? How many tokens are going out? Is the inputs greater or equal than the outputs? That's it, right? There's no really I have to get the hex of all the previous inputs or whatever. It's just a few opcodes in order to do this, to do these recursive checks. Then, of course, we have to start this somehow, because this would basically be require some input to have this already, but this would be impossible. So you kind of need a escape hash for the very first transaction, which would contain we would check the input out point if it is of a specific transaction, and then you can basically create as many tokens in a genesis as you want, and then after that you can never inflate it again. And you can see the overhead of this for a token is relatively small, 64 bytes, and that is roughly as much as ALP or SLP. So even though we get this minor forest level without doing cache tokens approach, it is still really quite compact, because the opcodes are really so much simple. But as I said before, it would be great if we could also expand the base of the token, because the previous one is just one time int, never increases ever. But it would be great. So the bottom part is cut out. That's the same as the other one. But here would be great if you have some other token ID, which are the mint batons. If you have any of them in input, which is exactly how SLP and ALP do mint batons, You just have to have them as input. Then you can mint as many tokens as you want. And then after that, you have no restrictions on the output sum. So you can just add as many tokens in the outputs as you want because this already succeeds. Right, so only check, do I have any inputs of the mint input token, so the mint baton token? And if yes, then I can create as many tokens as I want, which is the same as ALP does it, or SLP with mint batons. Then on top of that, one thing that we can do here is a infinitely inflatable token. So this is kind of like the thing we usually don't want to have, but for mint batons, this is extremely useful. So this basically allows us to be like, hey, you can, if you have at least one input of this token, then you can create as many as you want based on that. That's how mint batons work on SLP, or ALP actually. Like on ALP, if you have at least one mint baton, you can create as many as fit in the transaction size. Okay, more input batons. And this would be the same thing, right? So just with a few opcodes, we basically get what, and the previous one combined with those, we basically get what cash tokens really has to do in a roundabout way and only limited to a certain number. Here with the preambles, we just get that, which is a few opcodes. And this is like, I don't know, 6 bytes here, so very compact. And then there's more. I won't go into the details, but just to give you like a picture of like I basically came up with these just in an afternoon. So for example, and I think you can do that can you? Maybe. But something where like, hey, anybody can, if you have an old token, but you want to change the transaction ID or whatever, you want to upgrade it to a new token ID. But anybody who has the old tokens, they can seamlessly upgrade to the new token. So let's say anybody who has, I don't know, USDH, they're like, okay, we made an agreement with Tether. Anybody who's USDH, they can burn it, and in the same transaction mint USDT, whatever. Or if it's like the same company, then this becomes really easy. So this makes it such that if you are creating a new token on this protocol, but you're like afraid, like, I don't know, this is like the ultimate token or whatever, then you can be assured that like, no, if it isn't, like I need more rules, I need to add more things. You can just create a new token that seamlessly allows users to update their tokens to the new thing. And that's relatively easy. Another thing that's a little bit more complicated is a wrapped token, where and anybody can do this. It doesn't like someone has some token, and like actually I want to amend the token, more rules. I want to add more rules to it, but I don't have any cooperation with those. So let me just do a wrapped token where like you lock the main token into a UTXO, into the script. That's the like locked script, and it just sits there. And then when someone wants to, and then in that script you create the equivalent, like the same number of child tokens, like the new token that you want to create. So someone logs in like 10, I don't know, USDT, in that case is great, they lock it in there, but in the same transaction you can then create like 10 USDT2, or like your own wrapped USDT. You can send those around, you can use them, and then if you're like, okay, I use them enough, I have, I don't know, 10 USDT, you burn them in one transaction, and then you mint them. You burn them, and then the script that locked the old tokens, it releases them. So this here just checks, is the wrapper token fully burned? And if yes, then you get the tokens out. You can unlock the wrapped tokens. This is how basically every wrapped token works on like Ethereum or whatever. Except they have like a really complicated machinery to make sure that only the people who are authorized to do this. And with this protocol, it becomes like super easy to do. It looks a little scary, I guess, but it's just a few opcodes like this. As Matthew can tell you, if you actually write this kind of stuff, it becomes very, very big, very, very quickly. So this is surprisingly small. Then, this is the thing I mentioned before, is to kind of create like a DAO like something where it's like, hey, this is only accessible to token holders. So, and this is it. That's the whole script. So this is like this is where you send the money to, or like let's say XCC or some kind of token. And it's like, you take the XCC, you send it to this script, which contains the token that is like the shareholder token. So the token preamble hash is the token ID of the shareholder token. And then you compute how many tokens are there in the inputs. Let's say people collaborate, make a collaborative transactions. They all go into the inputs, and there's like, I don't know, 1 million of these tokens in the inputs. And then we only check if there's at least 1 million tokens in there. And that way the UTXO gets unlocked and it's sent to wherever the owners of the shareholder token decide it should go. And that's basically it. How much time do I have left? Okay, so this is just 10 seconds, basically. Okay, let me show off this. How do we get there? So there's basically 4 steps, I think, that we can do. First one would be testnet. But it might also make sense to start with Signet, which is like a proof of work-less blockchain. And it's just signed by some older. Core actually implemented this already in Bitcoin Core. It doesn't have any proof of work. It's just really easy to test. Testnet, I mean, people know testnet. It's like a chain. You also have proof of work, but very minimal. Then something that I think would be a really cool thing for if you actually wanted to start using this in any kind of practice would be an Avalanche subnet where we try out new transaction formats, because those you can shut down more or less. I mean, you can kind of deprecate them. There's not much work on those yet, but this is something that we could start thinking about. And basically the idea is that like you make like a transaction that looks like anyone can spend, but then Avalanche enforces that like the subnet rules apply to that output. And then, of course, at some point it would be great if the mainnet would get the transaction format in order to get the efficiency benefits. Because if everybody upgrades to that, and eventually we deprecate the old format, then we can build these hyper-optimized node processors. And from Project Hamilton, we know if you cut some corners, which they did, which we can't do, you can get millions of transactions per second, basically in an unlimited scalable way. And yeah, and if we want to, reach that vision that, Vin, for example, was presenting, was like, hey, this could be the ultimate thing, the ultimate token, like platform for stablecoins and everything. Eventually would be like, hey, we need to be prepared. We need to have something in the drawer to be like, okay, we're hitting limits. Here's a plan that we can do in order to like be able to process all of these transactions without falling over. Yeah. So 1 second. End it. Finn. All right. So questions?
Thanks.
We need the mic.
About except opcats, what all the scripts you present, do they need new and other opcode, or are all the opcode already available? That's just script presentation, or what you can do with new opcode potentially?
So you're asking if we need all of those opcodes that are listed in order to do? No. So these will all also be new suggestions for new opcodes. So opcat is already in eCash for a while, but all the introspection opcodes, we complete like the introspection opcodes, like to get the input, to get a specific input, specific output, and so forth. That is not part of the Preamble. This is all like an idea that you can do. This is not in Lotus. This is not. I mean, there's a pull request open for that, or this is a draft. Don't merge it.
There's a question from the chat, and maybe if we can maybe just make this the last question because we're running short on time here. Would an SLP or ALP token be upgradable to a new format to take advantage of the new functionality, like buy orders, or do you have to create a new token that would have this upgradability?
So yes and no. So no, because you still can't verify the tokens. Like just because we add tokens that can be verified doesn't mean the old ones suddenly also get verifiable. But what you can do is be like, hey, we deprecate this old token, and we basically just airdrop this new token to the same address as all the old holders, and then you can basically do an upgrade. It's just that all the new users, like the old token basically gets like this is no longer a valid token. Basically, it's no longer considered valid. So yes and no, basically. All right. Sorry for going over time, but yeah.
No worries. But we'll wrap it up there. Awesome. Thanks, Toby.